I'm going to talk about the commitments. James is going to talk about Cosmos some more, and eat some corn, and
some watermelon.
And I'm going to try to stay shady under my hat. But it's pretty sunny here. So I'm going to read my poem first, which I wrote earlier today. I wrote it this morning when I woke up, and it's called James's Copilot. I'm guessing that today will be another day I hit the street to help James choose which car to buy. But I don't want a car, of course. We went from car to SUV, and now a van's the thing to beat. Though I remain supportive, I don't want a car, I want a horse. Those stow-down seats within the van provide a lot of space to rest and live while we are traveling. That van was really comfortable. Those seats were awesome, so I can imagine they would suit us best, and man, that van had everything, and space that never would be full. Just so much empty space that I just saw as lack of family. I stowed those empty seats away, but I still knew those seats were there. It's strange how hard I had to try to think of other things to see, and yet that emptiness would stay. That van had too much space to spare. In fact, it had enough that I imagined it once broken down within the wilds where trees had grown around it like the cars I found on Grandpa's farm. I think I'll try to see I can escape this town within that van. And once alone, I might just keep that van around to live in all that empty space, my tiny house, Dodge Caravan, beside my horse that's grazing near, that's on my future perfect farm. A van could free me from this place, this purgatory where I can see nothing. There's just nothing here. And so, I just can't see the harm in bringing home that van, I guess. I'll sit by James's co-pilot, just thankful that he's taking me along to sit there by his side. James shouldn't pass up space for less. This van has space, a lot of space, that I'll try not to see. I'll sit and just enjoy the ride. So, we're still looking, of course. The commitments. Now, I don't know what year this was made. 99 or 91, one or the other.
Hard to beat.
I can't tell. Oh, there's two dates on here, and I don't know which one is supposed to be for the film and which, and frankly, I don't care. So, this is basically just a series of live, like music videos put together, and it's I don't know. It's just not for me. There's some talented people involved in this band. They're straight out of the Dublin ghetto, and they're doing R&B crackers from the 60s, it says. So that's boy, flies love corn.
So when they say R&B, it's basically soul music. Right?
It's soul music that they were doing.
I don't know why they use that designation, R&B.
No, either.
R&B back in the day was like what they called, I guess it was a transition from what they call race music. But it'd be more like Little Richard. I don't know. Like Tina Turner.
I should take that corn back inside. You see, what I did was I cooked it earlier in the husk, like normally on the grill, and then I took it out of the husk, and I put it in the fridge because I realized I had no idea when James was coming, and so I put it in the fridge, and then I decided, well, I'll just grill it a bit when he comes, and then that'll warm it up. But now I'm going to put it in the house, and it'll be cool again for when he eats. It doesn't make any sense. Would I recommend anybody watch this? No, not really. I really see no point in them having made this movie. And
Nostalgia, right?
I don't know. It's
A lot of people my age loved
it's a
60s soul music.
it's about a fake band, that the making of a fake band and then the falling apart of said
fake
fake band. Who cares?
The fake falling apart.
I didn't care at all, and it seemed kind of long. Like, and I can't find how many minutes it was.
It'd be sad if we're only 90 minutes long.
No, it seemed like 2 hours almost. I don't know. I can't find it on here.
Let's see if I can
I don't care. It's not worth it. So James is going to talk some more about
Cosmos.
and I am going to put this in the house away from these flies.
Appreciate it. They're not even going after the watermelon rinds at all.
Too much.
Yeah. So, I'll try not to be too cosmic when I'm dealing with Cosmos. So yesterday I left off with Neil DeGrasse Tyson. Neil DeGrasse Tyson. I always think of DeGrasse High. When I think of his name, that's why I mispronounce his middle name. So he worked his way through stuff from the moon all the way out to a red blob 13.4 billion light years away. It's not 13.4 billion light years away. I think he got most of the other stuff right. Some of the galaxies, if they're figured out, well, there was a galaxy, it was a Sombrero galaxy 30 million light years away. You might know that. A galaxy in a coma cluster 320 million light years away. I don't know. Theory starts to intrude, and the assumption would be if something's extremely redshifted from their point of extremely redshifted, then it's farther and farther away. The more extremely redshifted, the farther and farther away it is. The closer and closer it is to the edge of the universe as they see it. And it's laughable, this red blob. This red blob is something like a Magellanic cloud, something like, only considerably farther away than the large and small Magellanic clouds that are, they say, the companion mini galaxies to our galaxy, the Milky Way. The reason why they are redshifted, there's no doubt about it, is because they're small galaxies, and they actually have a very weak galaxy wind. They apparently detected something like a galaxy wind from the center of our galaxy, the Milky Way. And so we've got a larger than average galaxy size, or size galaxy, and there actually is, as I was explaining yesterday evening, there is a medium for light. I got a plasma physicist to do the work for me. I figured it was electromagnetic fields in one form or another for both. And he still doesn't know what I got him to figure out. So I was asking him, is it true what Alphen, a guy who won a Nobel Prize about 1971, dates to go back that far, some of the younger of you folks out there. Alphen said, along with several other things, that for a charged particle moving in a vacuum, including, of course, a charged particle moving in the vacuum of outer space, moving through that vacuum, that's a charged particle, moving through that vacuum is like trying to move through a circle. Understand, outer space is really, really thin. It's an attenuated vacuum. Very, very thin. I gather waves...
How did he know that?
Who?
Alfred.
Well, they'd know it from moving charged particles through vacuums here and there. You get vacuum tubes, all this, you know, made all over the place. Of course, you know, some of the more recalcitrant idiots in astronomy and astrophysics and stuff like that would say, well, you know, like in outer space, it wouldn't be like that. But I asked this plasma physicist if it were true, and he just kind of shrugged and said, yeah. Right? So he recognizes it, right? And then I said, what's slowing the charged particles down? And again, he just shrugged. So what's slowing down the energy basically coming out of my lungs heading towards the camera
I have to get really close to you to shade you.
is the air. That's the medium, particular medium. You know, there could be a door in between made out of steel, and that would have to be taken into consideration. It would be part of the medium, or we could be speaking underwater. If the camera worked underwater, with the water would be the medium for sound. But what it is what slows down the particles basically coming out of my lungs, and like they don't slows the energy coming down, and it's the medium. So you see, I got him to figure out what the medium for light was in vacuums. It's magnetic field. You got that? The astrophysicists out there, of course you're probably just ready to swallow your tongue with frustration and anger. But that's the way it is. You know, Einstein was wrong. Capital W, capital R, capital O, capital N, capital G, exclamation mark after, and exclamation al español before. Wrong. Wrong. It's like the Gong Show, only it's not gong, it's wrong. You got it wrong. Light is a wave, and the medium for light wave, at least in outer space, is magnetic fields. Okay? So there are, hence, two Doppler shifts for light. Not just relative movement between source and receiver of the light, this way or that way. Blue shifted this way, red shifted that way. It'll also be for source and receiver that are fixed distant from each other, and the medium, i.e. magnetic fields, moving either this way, blue shifted toward the receiver, or this way, red shifted. So you get this red blob that's supposed to be 13.8 billion years away. It's got a weak gravity wind, or a galaxy wind. We've got a huge thumping galaxy wind, and that overwhelms the galaxy wind coming from this blob that's way closer than 13.8 million. Is it billion? What is it? Billion light years away. 13.4, he said. Right? It overwhelms it, and it makes it so that stuff, the light coming from that little red blob, it makes it so it's red shifted. It's not. It's close. It's like a wee little blob. You actually see the outlines of the blob in the kind of telescopes that they're using. Jesus H God. I'm not even apologizing for cussing. I'm going to repeat it. Jesus H God. When I finally figured out, it didn't take me too long. I was going, why? The stuff that tends to be out at the edge of their universe as astrophysicists tends to be these asymmetrical blobs, like the Magellanic Clouds. And I'm going, why Oh, it's all theory ridden. It's not theory driven so much as theory ridden, like a pestilence. It's this theory, scientific physics theory has been, it physics is ridden with it, right? Riddled and ridden with it. You look at when Faraday was doing the work, and then when James Clerk Maxwell comes along, yeah, he did a good job, but he's decades after Faraday. He's a theoretician, James Clerk Maxwell. He comes after Faraday, and they kept on falling behind. You know, like they're looking at the Michelson-Morley thing, and for a while there's an experiment, and they're going, well, you know, like, well, what's happening there? You know, like it looks like the speed of light's the same all the time, blah, blah, blah. And then it took about, I think it was a little less than a generation, maybe 20 years, and Einstein comes along. Hey, I got this brilliant idea. You know, a little light bulb went off in my wee little head, and light is not just a wave, but it's a particle. No, it's not. And that's when things really started going wrong. 1905, really stupid. And then 1915, 16, 17, you know, like Einstein's going along and saying, you know, like gravity curves space, and guess what? Space is an abstraction, so is time. They're just abstractions. You can chop it up any way you like. Space you can put on a triple axis, you know, you can put it on a kind of square axis, but you can actually put it on axes that are based on hexagons, not cubes, well, not squares, but hexagons, and then like a hexagonal kind of three-dimensional figures with hexagonal sides. Now, it doesn't matter how you divide it up. You can say it's curved. Who cares? You can put curved lines in there. That's all an abstraction. Do you guys understand that? You're talking philosophy. You're importing huge, huge manure loads of philosophy into science when you start talking about science being, or space being curved, and time, time-space continua or continuum or whatever. You're bringing in huge, huge buttloads, well, I'll say boatloads for you folks out there, of philosophy in there. It's all horse manure. So now we're on to gravity, rule stars. This is William Herschel. Stars, not just the solar system. So he, you know, this is about 1800, a little after that. And then all of a sudden we jump to Albert Einstein. He's daydreaming in Italy. You know, I'm sick and tired of thought experiments. Do real experiments. I don't care about thought experiments. They were really big with Albert Einstein. Thought experiments, who does those? Philosophers. And leave that kind of garbage to philosophers. Okay? Came up with an earth-shaking idea. Yeah, it shakes my world, if not my earth, because it's shaking my sides. You know, every time I run across these thought experiments, I'm like, what would it be like if you were on a ray of light, riding on a... Yee-haw! Stupid. Okay, there's no fixed place in the universe. I don't think that was a really novel idea. You know, once you get Copernicus, what is that, 1543 or something like that, publishing his view of the universe, or at least the solar system. You know, the thought should have been, well, it's all relative. You know, in here, he's constantly saying, you know, like the Earth goes around the sun, and not the sun around the Earth. It doesn't matter. It's relative. It's more convenient because the sun you think of as being huge and not moving relative to the Earth. It's big and huge. It's got other things that are going around it. It just simplifies things. So basically, that's just applying Occam's razor to explaining things. You can explain it the other way. The sun goes around the Earth, and the planets go around the Earth, or whatever. You know, we could explain it, stuff going around Jupiter, and it just make for all sorts of complicated movements. But by complicating things and stuff like that, you could come up with an explanation. It would be hugely, well, not complex, but complicated. We just don't want to do that. The Copernican system, once Kepler came along, about 1600, then he was able to simplify it by explaining the orbits of the planets not as circles, perfect circles, but as ellipses. You know? All of a sudden, it's explicable. What would the world look like if you traveled at the speed of light? What would it be like? Who cares? You know, like this is just gospel truth. Nothing can go faster than the speed of light. Guess what? I don't think light can go faster than the speed of light. Just like you know, like if you drop something in the Earth's atmosphere, eventually it'll reach terminal velocity. Right? So I think there's a terminal velocity of sorts for light. But it's not a speed limit for everything. It's not a speed limit for neutrinos. It's not a speed limit for if you actually freed up neutrons. Well, not so much neutrons, but because they'd still have electrical charge. Something that doesn't have electrical charge, it's not moving through a vacuum, for example. It's what's going to slow it down. Remember what Alfvén said? For a charged particle. Moving through a vacuum, it's like moving through syrup. For a particle, it's not charged. Who cares? I don't think it would care. Just zip. No. You know, like there's this constant sort of thing. Like, okay, here's some light moving. You know, let's say around a cyclotron. Boom, boop, 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 boop. You know, like a charged particle, and you can almost get it to the speed of light. And let's say a train of charged particles moving around, right? Let's say it's like basically half and half. Here's moving here, and then it's zipping around. You know, I'm not interested in looking at it vis-a-vis the world. Or let's do a little thought experiment here. Okay? Here we got a not a cyclotron, but an accelerator, a nuclear accelerator, or a particle accelerator. Particle accelerator over here. It doesn't matter how far away they are, but let's say they're on the same campus or something like that. Okay, you accelerate a particle going speed of almost the speed of light. Can't quite make it there because it's a charged particle. And what happens is when it gets close to the speed of light, you know, it's like moving through a syrup, and the syrup gets thicker and thicker and thicker. That's what's happening. The equivalent of the syrup. Move one over here. Oh, see, like I'm not interested in the movement of this relative to the accelerator itself, or this one here. I'm interested in their relative speeds. And how would you compare them? You compare this speed to the accelerator, or the Earth that the accelerator is attached to. You compare this to the accelerator, or the Earth is attached to, and then you'd add those speeds together, and relative to each other, they're going faster than the speed of light. Almost twice as fast as the speed of light. You got that? That's an experiment that's probably done every day. Okay? Almost twice as fast as the speed of light. I'm not worried about just solely the speed vis-a-vis here or vis-a-vis here. I'm worried about the relative speed of each other. And how do you do it? You compare it to this thing and this thing here, and then you add the two together. That experiment has just confounded that whole thing of Einstein about it's an experience. If you put a particle accelerator on the moon, and you're moving stuff, you know, vis-a-vis a particle accelerator here, you'd be getting the same sort of thing. Doesn't matter how far apart they are, just so long as they're parallel. While you're doing the experiment, it's an experience. You got particle accelerators all over the world, moving stuff this way, moving stuff that way. The speed of light, the limit of the speed of light when it comes to just light stuff, because there's no electromagnetic field really messing these things around if they're far enough. So it's not slowing them down. If they start messing around with each other, they're going to slow stuff up. That's a different issue. So Einstein got that all wrong, and they've been getting it all wrong ever since. Okay? There's no fixed place in the universe. So what's the world look like if we travel at the speed of light? So he was talking, I don't know if it's in the notes later on, about if you travel to the stars at the speed of light, way away from the Earth, then come back, you won't have aged because time slows down. Did you know that, Pauline?
That's ridiculous.
Yeah. Because you see, what's the problem with that? The problem is all movement is relative.
Yeah.
When you fire a rocket up this year, you're actually you might as well look at it as the rocket moving the Earth down, and the rocket just staying still. It's all relative. Get that straight. You guys don't understand it. So you could actually say, well, like you won't age, you'll age, and those people of the world that you've kind of expelled your gases on and stuff like that, they get moved light years away from you. When they come back to you, wow, they won't have aged. So all you got to do is send one person way up in space. You wouldn't even have to send a person up in space. It could be like just a rocket that pushes the Earth down, relatively speaking. The rocket staying in the same place, and you wouldn't even have to sacrifice a person. All you'd have to do is send them way out and then way back, and then no one would have really aged. It's just like minuscule aging. See how stupid the whole thing is? You might think I'm stupid, but I'm not. Okay?
Oh, you're explaining it really well.
Yeah, I've known that for 30 years. Jesus H. God. Yeah, it's about the mid-90s. About the time I was working the cop shop, I figured that one out. Oh, my heavens. So he's talking, what a big hero, Mitchell, dark stars. Was he a contemporary of William Herschel? Something like that. So he's talking about dark stars. And so, of course, I suspect, Mitchell was using Newton's idea of light being a particle. And of course, a horse is a horse is a horse. If light is a particle or made up of particles, then those particles are going to be deflected by a huge gravitational field. It's going to be deflected by any gravitational field. But noticeably, presumably, by the huge gravitational field of the sun. So he actually envisaged, this guy Mitchell, John Mitchell, it's not that corrupt attorney that worked for CREEP, Committee to Re-elect the President, i.e. Nixon. He ended up, I think, going to jail. Probably not as long as he deserved. We saw a pretty good movie starring Sean Penn where he was portraying John Mitchell. And Margaret Mitchell, the maybe overly talkative wife of John Mitchell. I don't know if she actually might have been killed by people. I don't know if Nixon arranged for it, but maybe people who didn't want to see Nixon go down. Did she get killed? Can't remember. Not a very important person. Okay, so here's the thing. Let's look at the formula for gravitational force. So force equals G, small g, which is gravitational constant. Doesn't matter. But we'll put it in there. From your point of view, F equals G times m sub 1 times m sub 2 all over distance squared. Now we don't care